we're going to start these notes on and what this is it's actually a code word. It's code for solving systems of equations. And I did that on purpose. Oh my gosh, I can't spell. Anyway, I did that on purpose. What I did is I took the letters of systems of equations, I put it into something that jumbles up all the letters and kind of mixes them up, and turns it into code. And we have this title. We'll talk about that a little bit later. Okay, so last class we learned about how to draw linear equations where the highest power of x was 1, right? And all those equations had a straight line, and we were able to easily graph the equations. Now we're going to talk about how to solve these things called systems of equations, where instead of one equation, we actually have more than one or two equations. And instead of finding the value of x, we're actually finding the value of both x and y, okay? So the goal of these questions is to find what x and y values that work for both equations. If I plug them in, they would both be equal, okay? That work for both equations. Okay, and before we even talk about how to solve these types of systems, I'm gonna get kind of into my area of research in grad school. When I was in grad school, I did a lot of research in cryptography, which is essentially taking words and coding them into something that looks like this, like jumbled up letters. Okay, taking a look at this machine. Does anyone recognize this machine? Any of my history buffs? All right, this machine actually has a name. It's called the Enigma. Okay, and this machine is probably the most famous machines in the field of cryptography. It was used in World War II by the Germans. Okay, so the Germans used these in order to encode messages that they sent from one place to another. So if a German wanted to say, hey, my ship's coming this way, they would send the message, but in order to make sure that no one sees the message, they put in this machine and it jumbled up the letters into something that looked like this. Okay, so that no one could tell what their message was. Okay, now, gosh, where's my mind going? Now, the German enemies or the Allied forces, right? So it was the Allies versus the Germans. The Allies would intercept messages that they sent. So let me actually say point A to point B. The Germans would be sending a message from point A to point B, and the Allied forces would intercept the message halfway through and get this jumbled mess of letters. And what they did is they hired mathematicians to decode these messages to figure out what they actually said. Okay, so the Allied forces would get a bunch of jumbled little letters. Mathematicians would actually work out what the messages meant. Okay, the way mathematicians actually figured out what the messages were is they set up equations that look like this. They set up a bunch of systems of equations, but instead of just two equations and two variables, they would set up 51 equations. So like 51 equations with 51 different variables. I know, kind of crazy. So we would be solving a system of 51 equations with 51 different variables. It was very difficult, and it was actually something in the field of linear algebra. Okay, so if you ever take the class Linear Algebra SU, this is what you'd be doing, solving equations with a bunch of different variables and a bunch of different equations, figuring out what variables, what values work. Okay, now if you ever want more information about this, I suggest looking up Alan Turing. Okay, he was a British mathematician who worked with the Enigma. If you ever watched The Imitation Game, it kind of gives rise into how he did stuff. So that was happening in England. Back in the US, we had this guy named William Coffey. Okay, he was, that's a really interesting story. He was hired as a janitor and he figured out how to encode stuff. And he actually became, I think he was deputy director of the NSA by the time he finished his career. So two very famous, crypto mathematicians that really advanced the science. Okay, but we're not going to figure out how to solve equations with 51 variables in it. That sounds a little bit crazy. We're going to focus on equations that have two equations and two variables. Talk about how we solve these and how we get our values of x and y. Okay, moving on. So there's a couple of different strategies that we use to solve the following systems of equations. The first one is the graphing strategy, okay? And the strategy behind this is we have two equations, right? We have two equations that we want to find. What we want to do with these is we're going to graph both of them. So graph the equations. And we're going to see where they intersect, because where they intersect is where they both agree, right? And see where they intersect. So we did a little bit of graphing last class. Why don't we try to graph these and see what happens? Okay. So we have y equals 3x plus 4. Let's try to graph that one first. What's the slope of this equation? Not 3x, but just 3, good. And what's the y-intercept? 4, good. Remember, the slope is attached to the x, the y-intercept is by itself. Okay. If I want to graph this equation, I would first graph the y-intercept, oh my gosh. Okay, and the slope tells us rise over run, right? So the slope I can write as 3 over 1. I can rise up 3, run over 1. Unfortunately, if I do that in my graph, it looks like I'm going to run out of space. Any other way I can draw my next point instead of going up 3? Yeah, you can go down 3, and would I go to the right or left? To the left, good. So I can go down 1, 2, 3, and go to the left 1. And that's the same as rising up and going over 1. Okay. Now I can do that a couple of times just to make my graph look a little bit nicer. Okay. And once I have my points on my graph, I can connect them. So I can kind of connect my points with a line. Okay. All right, so I graphed the first equation. Let's graph the second one. This one has a slope of 3, right? And a y-intercept of -2. Okay. So same deal, right? I'm going to plot my y-intercept, go up 3 over 1, go up 3 over 1, go down 3 over 1. Okay, and I can connect these with a line. Okay, well, it said my strategy was to graph the equations and see where they intersect. Do these graphs ever intersect? No, and why is that? Claire. Yeah, they have the same slope, right? These two equations have the same slope. They're never going to touch each other. They run in parallel to each other. These are examples of parallel lines. Okay, and they never intersect. Okay, so how many solutions do we have to this equation? 0, right? This is a system with no solutions. Nothing, no values of x and y will work for this system of equations. Okay. So just a little note that yes, we can actually not have a solution to some of our examples. Okay. Any questions so far? Why don't we do one where there actually is a solution? Let's move on to example number 2. Okay, so here we have 2 equations. Let's try to graph this one. The top equation has a slope of 4. Wait, is it 4 or -4? Good. And a y-intercept of 2. So graphing that would be plotting 2, going down 4 and over to the right 1, right? 1, 2, 3, 4, 1. And okay, I drew that line. Let's see if I can connect these pretty well. Okay, it's about right. Okay, I can graph my other line. What's the slope of my second line? Not 0, but -1, right? There's still an x. If it was 0, there wouldn't be an x. Okay, so the slope is 1, but it has a minus sign, so it's -1. The y-intercept is -3. Okay, plotting this one, I'm going to plot my point at -3. I can go down and over 1, go up and over to the left 1, and my graph is going to look like this. Let's see if I can do this right. Oh, that was bad. Let's see if I can do it a little bit better. Nope. Let's see. That works. Okay. Looks like my 2 lines definitely do intersect here, right? Let's try to see where they intersect, about here. Okay. Here's the problem with solving these equations with graphing. When we graph the equations, sometimes they don't intersect at a really nice point. Sometimes the point is kind of off kilter a little bit, and it's kind of hard to approximate where it is. Let's just see what our answer might be. And then later we can talk about a better way to go about this. Okay. So what x value do you think this purple point is at? That's the y value, but what about the x? Yeah, that sounds about right. It's like, it's not 2, it's almost there. So maybe 1.9 works, right? And Jules, what did you say about the y value? Yeah, but negative, right? So negative 4.5-ish sounds about right. Okay. This would be the answer to my system. Now, this wasn't very accurate, right? We graphed it. We don't really know if our decimal places really work. Let's talk about a little bit more of a precise way how to do this, okay? So on a tester quiz, I'm probably not going to ask you to graph, solve something by graphing, just because the answers can be all over the place. Okay. Here's a more precise way to solve systems of equations, and we call this way elimination. Okay, so elimination is a more precise technique, and it's more algebraic, so it involves a lot of algebra. Okay, first of all, when we look at this equation, I wrote it wrong. There should be an x after the -16. Totally forgot about that. Okay. The first step to doing these equations is to make sure that everything's stacked on top of each other. Okay, so I want all the x's stacked on top of each other, all the y's on top of each other. So let me just write that a little bit neater. 8x minus 6y equals -20. And I'm going to make my -16x and my 7y and my 30 right below each of these values. Okay. Now, when I solve these equations, I kind of have a step-by-step process of doing this. The first thing I want to do is, I'm going to write this down. I want to make sure that one of my variables, so either x or y, has the same number but a different sign. Okay, so make sure the coefficients, and when I say coefficient, I mean the number attached to the variable. Okay, make sure the coefficients of one variable match, but they have different signs. I know that's kind of wordy. Okay. Looking at this process, the way we do this is we're going to multiply everything in one equation by the same number. Okay. Now, oh, wow, that was interesting. Okay. Now I'm going to do this step this time, and then I'll let you try this on your own. I kind of noticed that 8x and 16x can be transformed into each other by multiplying by 2, right? I can kind of multiply 8x by something to get negative 16, okay? I'm going to take this 8 and multiply it by 2 because I know it's going to become 16. I'm not going to multiply by negative 2 because I want negative 16 to be positive 16 in the other equation. Okay? Now, if I do something to one thing in an equation, I better do it to everything else, right? So I'm going to take every single of my coefficients and multiply it by 2. Okay. So the top equation becomes 8 times 2 is 16x. Negative 6 times 2 is negative 12y. And negative 20 times 2 is negative 40. Okay. Now I didn't do anything to the bottom, so the bottom stays the same. Negative 16x plus 7y equals 30. So does everyone kind of see how the coefficients of x are the same, but they have different signs? Yeah. Okay. Here's where the funky trick goes. I have everything stacked on top of each other. When I stack things on top, I can add or subtract, right? Do you think you're going to add or subtract these two equations? I'm going to say add, and you'll see why. I think I know why you're saying subtract. I think we're on the same page here. Okay, let's just add the two equations. Okay, which means I'm going to add the coefficients of all the different variables. What's 16 plus negative 16? 0. So I have 0x. Okay. What's negative 12 plus 7? Negative 5. Good. And what's negative 40 plus 30? Negative 10. Okay. Do you see why I added the two equations? One of them went to 0, right? Now, if you want to try subtracting it, you can try it, but one of the variables isn't going to go away.
So you're just always trying to cancel out one of the variables.
So in this case, I wanted to cancel out x because they both kind of matched. So I decided to add them. Okay. Well, 0x is 0, right? So I can just kind of get rid of that. And I'm left with negative 5y, oh gosh, equals negative 10. Okay. How do I get y by itself? Good. Divide by negative 5 on both sides. And we get y equals 2. Am I done?
No.
I got y, but there's another variable in here, right? There's an x, right? Does anyone remember how to get x?
Plug the 2 in and then plug the 2 in for y and then solve for x.
Perfect. Okay, so what we're going to do as our next step is I'm going to pick an equation, and it doesn't matter which one I'm going to pick. Okay, so pick one equation, and it doesn't matter which one. Okay, once I pick an equation, I'm going to plug in whatever I found. So y equals 2. Okay, so looking at my two equations, it looks like the top one is easier. So I'm just going to pick that one. 8x minus 6y equals negative 20. Okay, plugging in y equals 2, I'm going to get 8x minus 6 times 2 equals negative 20. Okay. 6 times 2 is 12. I'm here. I have 8x minus 12 equals negative 20. Should I divide by 8 first or add the 12 first? Add the 12 first, right? So we will want to get rid of the addition first. So let's add 12 on both sides to get 8x equals negative 8, I think. Okay. And then we can divide by 8 on both sides to get x equals -1. Okay. So many ways you could write your answer. I would totally accept circling the x and the y as my answer. That's totally fine. Some people like to write their answer in an ordered pair where the x goes first and the y goes second. So -1, 2 is also a way to write your answer. But I am fine with circling the x value, circling the y value, and being done. Any questions on example 3? All right. I'm going to give you a few minutes to work on example number 4. I know it's a lot of algebra. I know it's a lot compared to what we've been doing before, but I think we've got it. Here. Did I get Ashley to write up your answer? All right. Ashley did a very good job of writing up her answer here. Do you kind of want to take us through your steps here?
The bottom equation by 6.
Mhm.
So it cancel out. And then
Mhm. Oh my gosh. Mhm. Good job. Okay, so very nice. There were kind of 2 ways you could have gone about this question. I've seen people do either way. Ashley multiplied at the bottom equation by 6, which is great. Now, yeah, sorry, which is great. Now, another thing I saw people do is this is an alternate method, which is just as easy as multiplying by 6. You could also see that the 12y and the 6y kind of differ by a factor of 2, right? So you could have multiplied the bottom equation by 2 to make the 6 and the 12 match. But since they're both negative, maybe I might want to multiply by a -2 to make one of them negative and one of them positive. So that would have been okay. Any questions on example 4? Okay. Do we feel like we need a little more practice with this? Yeah, let's do a little bit more practice next class with this. I do want to talk about the next thing before we do the quiz review. Looking at the time, but next class we will do more examples on this, so it'll get a little bit easier for us. Okay. Flipping our page. Systems of equations don't have to be just regular questions. We're in a statistics class, so we definitely have to deal with word problems and things applied to real life scenarios. Some applications of this is kind of like real life applications involving money. Okay, so let's just take a look at this question. We have that the cost for admission to a concert is $162 if we have 12 children and 3 adults. Okay. We also know that someone came in and bought 8 children tickets and 3 adult tickets, and the cost was $122. We want to find out how much it costs for each adult and each child. So we don't know exactly the prices for each adult and each child, but through this information, we can actually figure out the individual prices. Okay. So first thing I want to do is when we deal with these questions, I always like to write my variables, okay? Because I want to have a variable that resembles the question so it's not hard for me to do the question later on, okay? We want to find the cost for admission for an adult and a child, okay? Can someone give me a reasonable variable to stand for adult? A, right? A sounds like adult, and I won't get confused later in the question if I see A, right? Now, what do you think child is going to be? C, right? Okay, so that's kind of the most important part, because I feel like setting up the question is very hard, and if you don't have variables that resemble the question, it gets a little bit more difficult. Okay, so first sentence says the cost for admission of a concert is $162 when we have 12 children and 3 adults. Is there anyone who can come up with an equation that kind of says what the first sentence says?
I'm guessing 12 could be A, B, C.
I think you flipped them, but
Um,
you were close. So there's 12C.
3 is A,
Uh-huh.
and equals 122,
Not 122, but 162, right?
162.
Mhm. So, and I think you meant to put a plus in the middle too, right? Yeah, but that's exactly what the question's saying. We want 12 children and 3 adults is 162. Does that make sense? All right. What do you think the second sentence turns into? Jules? Perfect. Okay, so we have a system of equations. Now it's just like the regular equations that we've been solving. Okay. Taking a look at this. Now, I said before that we want the coefficients of one variable to match, and it looks like that we already have that happening. We have a 3a and a 3a. They match, but what do I have to do with them?
Subtract.
Yeah, we can subtract them, but let's go with the kind of conventional way of doing this. I want them to match and have different signs, right, Ellie?
Which is most part of
Perfect, right? So does it matter which one I multiply by -1? No, right? Because both of them have a 3a. Just to make things interesting, I'm gonna multiply the bottom one by -1. So I'm gonna take every single coefficient and multiply it by -1. Okay, now you can multiply the top by -1, that's totally fine, but let's just do the bottom one. So on the top, we have the same equation. Okay, on the bottom, we have -8c minus 3a equals -122. Okay. Now we're at a point where we can add the equations. Okay. All right, what's 12c minus 8c? 4c, right? What's 3a minus 3a? 0, good. And what's 162 plus -122? 40, good. Okay, so I just multiplied, or sorry, I just added the top and bottom together. Now 4c plus 0 is just 4c. How do I get c by itself?
Divide 4 by both sides.
Good, divide 4 on both sides. C is equal to 10. So what I just did is I found that the cost of a child's ticket is $10. Am I done my problem yet? No, right? Because I need to find how much the adult tickets cost. Looking at my two equations, I think the bottom one is easier to plug in just because there's an 8 there. So I'm going to take my C. I'm going to plug C equals 10 into one of my equations, and it doesn't matter which one it is. So I'm going to plug it into 8c plus 3a equals 122. Okay. 8 times 10 plus 3a equals 122. 8 times 10 is 80 plus 3a equals 122. Okay. What should I do? Divide by 3 or subtract 80? Subtract 80. Remember, subtraction goes first here. So 3a equals, is it 42? Okay. And to get a by itself, all we have to do is divide by 3, right? So a equals 14. I know that an adult's ticket costs $14. Any questions on example 5? I don't know if we have enough time to work on example 6. This is where I left off in my last class. I do want to do the quiz review though. How about we leave example 6 for next class? And we'll do the quiz review now. None of this is going to be on the quiz review. The quiz review is on stuff that we did on Monday. We'll do plenty of practice on this stuff